Welcome to this short video about the formal, or as it's often referred to, the epsilon delta definition of the limit of a function. Let's consider the following problem. The limit of 5x plus 3 as x approaches 1 is equal to 8. This mathematical statement tells us that when values of x get close to 1, the values of 5x plus 3 get close to 8. Let's look at this graphically. On the screen, you will see the graph of f of x equals 5x plus 3. As we trace the function and approach x equals 1 from either the left or the right, the values of f of x equals 5x plus 3 seem to get close to 8. The questions become, how do we define close, and what do we mean when we say the values of f of x equals 5x plus 3 are close to 8? Well, by close to 8, we mean that the distance between the values of f of x equals 5x plus 3 and 8 is small. Mathematically, we define the distance between two numbers as the absolute value of their difference. For example, the distance between 8 and 2 is the absolute value of 8 minus 2, or 6. The distance between 8 and negative 2 is the absolute value of 8 minus negative 2, or 10. Therefore, in our example, the distance between f of x equals 5x plus 3 and 8 is the absolute value of 5x plus 3 minus 8. And what do we mean by small? Smaller than any positive number. In mathematics, we often use epsilon to represent an arbitrarily small positive number. Therefore, when we say the values of f of x equals 5x plus 3 are close to 8, we write the absolute value of 5x plus 3 minus 8 is less than epsilon. But we should also observe that we don't expect the values of the absolute value of 5x plus 3 minus 8 to always be small, only when the values of x are close to 1. Using the same logic, the values of x are close to 1 when the absolute value of x minus 1 is small, or less than some other small positive number, delta. That is, when the absolute value of x minus 1 is less than delta. Therefore, by the limit of 5x plus 3 as x approaches 1 equals 8, we mean that for any small number epsilon, there will exist a small number delta such that the absolute value of 5x plus 3 minus 8 is less than epsilon whenever the absolute value of x minus 1 is less than delta. Again, looking at this graphically, if we wish to make the values of 5x plus 3 closer to 8, we can make the values of epsilon smaller. And in order to do this, we must choose values of x closer to 1. That is, make values of delta smaller. So in general, what we mean when we write the limit of f of x as x approaches a equals L is the mathematical statement: for any small epsilon, there will exist a small delta such that the absolute value of f of x minus L is less than epsilon whenever the absolute value of x minus a is less than delta. This is the epsilon delta definition of the limit of a function. Now, to prove that the limit of 5x plus 3 as x approaches 1 is equal to 8, we must choose epsilon and find delta. So let epsilon be greater than 0. And consider the absolute value of 5x plus 3 minus 8. Simplifying, the absolute value of 5x plus 3 minus 8 equals the absolute value of 5x minus 5, which is equal to the absolute value of 5 times x minus 1, which is equal to 5 times the absolute value of x minus 1
But since x minus 1 is less than delta, this is less than 5 times delta. So if we let 5 times delta equal epsilon, then the necessary delta is epsilon over 5. This provides us with a formula for finding how close to 1 we must be in order for 5x plus 3 to be close to 8. Let's try another example. Similarly, the limit of x squared minus 9 over x minus 3 as x approaches 3 equals 6 tells us that when the values of x get close to 3, the values of x squared minus 9 over x minus 3 get close to 6. Therefore, we must show, for every epsilon greater than 0, we can find a delta greater than 0, such that the absolute value of x squared minus 9 over x minus 3 minus 6 is less than epsilon whenever 0 is less than the absolute value of x minus 3 is less than delta.
So let epsilon be greater than 0. We want the absolute value of x squared minus 9 over x minus 3 minus 6 to be less than epsilon. So consider the absolute value of x squared minus 9 over x minus 3 minus 6. Simplifying, so if we let delta equal epsilon, we have shown that there exists a delta for every epsilon that satisfies our inequality. Here's a little more difficult example. Let's consider the limit of x squared plus 5x plus 6 as x approaches 2, which is equal to 20. So let epsilon be greater than 0. Now we must show that the absolute value of x squared plus 5x plus 6 minus 20 is less than epsilon whenever 0 is less than the absolute value of x minus 2 is less than delta. Now consider the absolute value of x squared plus 5x plus 6 minus 20. Simplifying, we see that this is less than or equal to the absolute value of x plus 7 times the absolute value of x minus 2. Since we want the absolute value of x minus 2 to be less than delta, we have, but the size of the absolute value of x plus 7 depends on our choice of x, so let's restrict delta to be less than 1. Therefore, x is between 1 and 3, and we know that the absolute value of x plus 7 is less than 10. As a result, the absolute value of x squared plus 5x plus 6 minus 20 is less than 10 delta. So if we choose delta to be equal to the minimum of 1 and epsilon over 10, our inequality will always hold, and we have a method for finding delta given any epsilon.